Welcome back to my ML Engineering Starter Pack, where I'm talking about 11 topics in machine learning engineering. Today we're talking about data structures, probability and stats, and ML algorithms. By the way, if you want to learn more full-stack data science, you can check out my Patreon page and help support the channel. You can also sign up for my newsletter there, and I only send one email a week when I upload a new video. So let's get to today's topic of data structures. I'm going to start by looking at this big O cheat sheet. This will help contextualize some of the stuff we're about to talk about. On the y-axis here, we can think about this as time or size. For example, size of a data structure like an array. And on the x-axis, we have number of elements. A linear algorithm, which is order n, is depicted here. It's a straight line, and none of these other lines are straight. So like an order n squared algorithm, you can just visualize here how much worse it is in terms of performance for time or size. Whereas something like an order log n algorithm is depicted down here, and it's much flatter than a linear, so it's much more efficient. So let me give an example of order n versus n squared. Order n would be if we had, say, one for loop x naught to xn. This would be order n because we have to say x0, x1, x2, x3, and we have to do n operation. If inside of this loop we had another for loop, then there were n y elements and we were processing these guys. Now for each of these n, we have to do an additional n. This is how we would get n squared algorithm. Let's say what we were doing was, instead of a for loop, we did some other operation calling f of x. And let's say f of x here is logarithmic. Then we would get an n times log, and that would perform better than n squared, and that's actually visualized here. So I hope this strengthens your intuition as to these big O notation. Lastly, I want to talk a little bit about order of magnitudes in general. This is a way of us saying roughly how fast or how big something is. Order of magnitude of 1, somewhere around here, and we're kind of in and around this range. So if we went up an order of magnitude from that, we would go into order 10, and now we're kind of in this type of range. Let's go to 10,000. So it's a way of generally expressing how fast or how big something is or how accurate something is. You could also go the other way, 0.001, kind of in this little range. So whereas notation like order n, log n, so whereas these are used to talk about data structures and algorithms, these ones are more used to talk about data size. In the previous video, I had a data set size that was like 16,000 rows. That is on the order of 1e4, and we saw how fast that data set loaded. But then later, we were using a much bigger data set with DAS, and that data set was on the order of 1e to the 8. So let's get into data structures. These are foundational and largely abstracted so that we don't have to think about them. But there's a real benefit in going back to fundamentals and practicing some lead code problems. The first data structure we'll talk about is an array. This is a collection of elements identified by index. And I'm going to do a Python demo, define an array. So we can do array access. That would be like array of 2. This type of access is order 1 because arrays are identified by index. And we're saying we want the second index. So we just go to the memory location for the second index. Next, let's do an insertion. And say 3, which is from the order of 1 to the order of n. Sometimes you have to shift the data around in memory, which would take n time the size of the array because you might have to shift everything. Let's do a delete. So we could say array.pop, and I'll just pop the element off the end. But we could also pop a specific index, like the second index. The delete operation is also from order of 1 to order of n. Lastly, I'll do a search. And a search is order n because we have to look through each index. Is 4 in the array? It is. This number in the array, it's false. And this would be order n because we have to look through each element, assuming there's no indexes on the array, which again is a higher level data structure. Next, we're going to look at a linked list. This is a sequence of nodes where each node points to the next node. It's no longer accessed by index, but it's accessed by relation between the elements. For a linked list, access is order n instead of order 1. To get a specific node, we have to search through, at worst, every other single node as we follow the relations. So let's create a linked list and then define some operations on it. Here I have a list node object. It's going to have a value and then a next pointer, which is going to point to the next node. And now I have some helper functions that we're going to use to work with our linked list. Jupyter, and paste all of this. So I'm just having this head object, and this is my list node. So it'll have a value. And if I look at the next item, it's going to be another list node, and that'll have a value. And if I keep going like this, that's it. This is how we would traverse our linked nodes. I can't say something like had index 3 is listed by relation to one another. First, we're going to insert an element. Insert it after the second node. So at worst, this is order n. As I said, head.next. But if I wanted to insert at a different location, I would have to keep traversing this. Lastly, I'll show an example of searching. So let's see if 3 is in here. I start at the head, and I'm saying, well, the current is not none, and we're iterating over all of our values in the linked list. Again, this shows why it's order n at worst. Now let's talk about stacks. In stacks, you're only allowed to access the thing on the top. So an undo mechanism is perfect because you only ever want to undo the last change. It would make no sense to undo something you did like 5 changes ago. Another interesting idea is when you open a bracket, you need to close that bracket. So you can put that bracket onto the stack and check that that's been done properly. In this case, operations are free. You can push things onto the stack with order 1. You can pop them off the stack with order 1 or look at them with order 1. Let's use DQ in order to demonstrate this. Create a stack. It's actually a double-sided queue, but we're going to pretend it's not. We're going to pretend we can only get off the top like it's a stack. So I could peek at that, just look at the top element, insert something. So I'm just going to append. I'm going to just push something on top of the stack, and there's my 6 value. I could also delete something, and in Python I would say pop. And so, oops, I pushed by accident, but I would say stack.pop. 6 is out. Let me do it again. Let me do it again. There's a 5. There's a 4. So now we have 1, 2, 3. Lastly, I can do search, and I can say is 4 in the stack. Now, search is not really a thing you do with the stack, or at least not for free. You'd have to like peek at each element below. In principle, you'd have to unbuild the stack and rebuild it again. So this would be a really expensive operation. It's not something you'd want to do with a stack data structure. Next, let's talk about queues. Queues are like the opposite of a stack in a way. You do push things on top of them, but then you can only get things out the other side. Good use case is web crawling. Look at a web page, you get a bunch of URLs, and you put them in a queue to be crawled later. These will just pile up in a first in, first out order. These are also free. Queuing them up is order 1, and taking them off the bottom is order 1, because we know exactly where to look for these things. So let's implement this using DQ. Create another demo data set. Now what we would want to do is look at the 0th element rather than the last element. Append something. But now when I want to get elements off, I want to pop them off the left side. Q.pop left. And that's going to take out my first element. Now I'll get the second element, and that's out of my queue. And again, I could go ahead and search in the queue, but this would be subject to the same problem as before, where I'd effectively need to destroy and rebuild my queue data structure if I wanted to do that. For searching, the king of data structures is a hash table. And operations are also free on this, where you can insert with order 1, you can delete with order 1, and search with order 1. It's not exactly true because, for example, you could get a hash collision, which has to be dealt with. But roughly speaking, and for the purposes of understanding these conceptually, we can think about these things as being true. In Python, hash tables are dictionary objects. Instantiate this hash table, and I'm going to insert a few things. So if I want to access the value for key 1, that was done in order 1. So for example, if I had a loop, I'm going to create a bunch of random characters here, and I say hash table a equals whatever. If the length of this is n, then this is an order n thing to do. I'm allowed to add these for order 1. So this whole thing runs at order n. If I wanted to get these, this also is just going to run in order n, because this operation here is order 1. And same with this. Searching is order 1. I just know if that's in the hash table or not because I can just check for that data directly based on the hash of my key. The last 2 data structures I'm going to talk about are trees and graphs. So a tree is a hierarchical data structure with nodes. An example of this is a binary search tree. We can think about trees in the context of databases because when we index things in databases, we often use tree structures under the hood in our indexes in order to do that efficiently. That's why we can do lookups and things like log n time, because we're representing data in this type of way. The last data structure I'll talk about is graphs. This is a collection of nodes and edges connecting pairs of nodes. This is different than a tree. For example, above, the 2 could not connect to the 3. But in the graph algorithm, that would be okay. The usage here is like a network representation, like friends on Facebook or followers on Twitter or something like that. And the operations here are going to vary depending on what we do, and graph algorithms can get really complicated. But in some cases, they could be really useful and efficient and the correct way to solve your problem and model your data. I would suggest going to LeetCode and practicing the problems there to get an intuitive and practical understanding of how to use data structures and algorithms.
Attention, brave data scientists! The kingdom is in peril, and only you can save it. Join us on an epic quest to get a forecasting app into production, from the realm of higher thinking to the land of Jupyter notebooks and data exploration, through the kingdom of NeoVim and implementation, and finally to the castle of production APIs and Streamlit. Embark on this journey and equip yourself with the skills to train and productionize a demand forecasting model. The kingdom awaits. Are you ready to become the hero we need?
The next topic is probability and stats. So let's consider you're playing Dungeons and Dragons and you're rolling a d20 dice, and the probability of a critical hit is 5%. What is the probability of rolling 2 20s in a row, of getting 2 critical hits? What's the probability of doing that 3 times in a row? The way to do that is to multiply the probabilities together. So that's what I'm doing in this dictionary. We can see the probabilities of doing it twice in a row is just 0.05 squared, which is less than 1%. Doing that 3 times in a row is 0.01%. Next, let's continue to build up an intuitive understanding of probability by talking about conditional probability and Bayes' theorem. I'm going to start with this formula here. PT is going to be the probability of getting tested positive. Well, we could break that down into conditional probabilities. The probability that you test positive is the probability of testing positive given that you had the disease, probably really high, and then you multiply that by the probability that you have the disease to start with. That's just a conditional part of the total probability. The other option is that you don't have the disease. So what's the probability that you tested positive given that you don't have the disease times the probability that you don't have the disease? And this is how we can break down conditional probabilities. And here I'm just creating some numbers for those. Let's start with PT given D. What's the probability you test positive given that you have the disease? 99%. Pretty much guaranteed. And then we multiply that by PD, the probability in general that you have the disease. Pretty low likelihood, random person, no reason you should have the disease. Let's say it's like 1 in 100. Next, what's the probability you test positive given that you don't have the disease? Pretty low, false positive reading. And then lastly, the probability that you don't have the disease is 1 minus that you do, so it's like 99%. And so this would give us PT, the total probability of a positive test. So lastly, let's look at Bayes' theorem, and that's here. So we say the probability of having the disease given that you have a positive test. That's really what we're interested in here. I got tested for something. It says it's positive. What are the chances that I actually have this? That's going to equal the probability of a positive test given that you have the disease, which we've already talked about. We know that value, times the probability that you have a disease in general, which we said was like 1%. And then dividing by the total probability of like a positive test, which we just calculated. So let's review. We want to calculate this PD given T, and we need to know the probability of a positive test given D, which we're saying is like 99%. We're going to say the probability that you have the disease in general, 1%. PT, which we're able to calculate using the formula we just talked about with conditional probabilities. And this will actually give us the probability of having the disease given a positive test. So let's go ahead and calculate this. So we're seeing that the probability of having the disease given a positive test is only 16%. That seems really low. I got tested positive, only a 16% chance. So what's going on there? Well, if we look at Bayes' theorem, we're having this probability of having the disease. This is like a prior probability that we think you have the disease. It's possible that if you're getting tested for something, you have more than, what did we say PD was? It was just 1%, but maybe if you're getting tested for something, PD should be bigger for you. We should be saying there's a higher prior probability on you having the disease. In fact, maybe because of your lifestyle factors, there's like a 50% chance that you have this. Maybe it's even higher, but let's say it was 50%, and then let's go ahead and recalculate this using Bayes' theorem. So I'm just going to go ahead and grab all of this, and actually I'm just going to set this to 50% for the probability, the prior probability. And now in this case, you have a 95% chance of having it. We can see how much setting good priors can affect our outcomes when we're doing Bayes stuff. I love Bayes' theorem, and I hope you like that example. Next, we're going to talk about standard deviation, and this is used in statistical testing. For example, k-fold validation when we're doing machine learning. So I'm going to go ahead and run this entire example. We're going to look at what the results are. So we have a sample data set, and at this point, if you haven't already done this, I'd encourage you to grab a pen and a paper so you can write these equations down. And here what we're doing is defining a sample data set, and then I'm calculating the average of that data set by summing it, dividing by the length. And now what I want to do is calculate something called the variance. The standard deviation is just going to be the square root of that variance. So really the variance is where we calculate the interesting quantity here. We're summing the differences between each value and the average for each value in our data. After we look at the difference, we don't really care if it's below or above the average. And so the way of expressing that mathematically is by squaring it, because that way if you square a negative number, it becomes positive. After we do all of that, we just divide it by the data because we want the average quantity, and then we're taking the square root after. So we're sort of correcting for that squaring that we did in here to give us something that's going to have the same units as our data set. So when we see a standard deviation of like 3.6, we know that that's in the same units as whatever we had in our data set. And the standard deviation has interesting properties, like the percent of data that lies within plus or minus 1 standard deviation, or plus and minus 2 standard deviations. Next, we're going to look at the correlation coefficient. This is useful when you're doing feature selection or looking for multi-collinearity, seeing how well your columns are related to each other. Sometimes this could be useful if you have columns that are highly correlated with your target variable. They could be really useful for predicting that. Sometimes this can be a problem. If you have columns which are really highly correlated with each other, this can like break or invalidate assumptions of machine learning models. So let's again run this entire example. We're defining a couple sample data sets, and I'm going to compare these. And you can just see looking at them, I have 1, 2, 3, 4, 5, and then 2, 4, 6, 8, 20. So they're sort of trending in the same direction, but these ones are negative. So we're going to see how that comes out with the correlation coefficient. First, I calculate the average of each data set, and then I calculate the variance and the standard deviation. We'll use this standard deviation when we calculate the correlation coefficient. But first, we're going to calculate the covariance, which doesn't depend on the standard deviation. In order to get the covariance, think about merging these, and we're going to iterate over them together. So in the first iteration, we're going to be looking at 1 and negative 2, and we're going to say, what's the difference between 1 and the average of x, and then multiply that between the difference of negative 2 and the average of y. We do that for each element and then add up all of those differences and divide it by the length to get the average difference. Lastly, we're correcting this using the standard deviations. So we're going to divide this covariance by the product of the standard deviations. And what this does is normalize our result. So we're going to get something in between -1 and +1. I'm also doing this with NumPy just so we can show how this can be done in one line as opposed to coding it all up manually. And we're comparing these to see that they are producing the same result. And what we can see in this case is it's very close to -1. So these are inversely correlated, close to -1, almost as good as we can get. If we saw a result close to +1, we'd say that they're highly correlated with each other. And if we got a result close to 0, we'd say that they're not correlated at all. So lastly, I'm going to talk about the normal distribution. This has use cases around modeling assumptions. For example, linear regression assumes that residuals are normally distributed. Another example is for feature engineering, where we will want to normalize our variables before feeding them into our machine learning algorithm by going through a process called normalization. You can think about normalization as rescaling your x-axis on your distribution. So like the other demonstrations in this section, I'm going to do this by hand with Python, and then we're going to also use SciPy to do it in one line, and I'm going to compare these two things with Matplotlib. Here's our result. We can see that they both match perfectly, and look at the x-axis. This is -4, this is -2, this is 2, this is 4, so this is a normally distributed data set. When we go through a process of normalization, we're pushing data so that it has these same x-axis values effectively. Although it won't look perfectly normal, that's the whole point. Every data set is going to look different. So the distribution will still look a little bit different than this, but we're just sort of like pushing the x-axis into this normal range. And you can see why that would be beneficial for machine learning, because now the data is at the appropriate scale that the algorithm is expecting. And now let's just talk about what we did here. So the manual implementation looks like this. The normal distribution function. It's going to depend on the mean and the standard deviation. These are parameters of the function. And this is how the function modifies those parameters to get out the result. Notice we're using pi in here, and we're using the exponential as well. So now we're generating a bunch of x values, and I'm evaluating this function for each of those values given some mean and standard deviation. We're going to also use SciPy to do that. So this probability density function for the normal distribution, and then we're just comparing those. So that's the last probability and stats thing that I want to talk about today. The last topic for today are ML algorithms. I'm not going to talk about how these algorithms work with math, but I'm just going to show some hands-on examples of a few different types of algorithms. We're going to look at supervised and unsupervised learning, and I'm going to talk about algorithms like linear regression for regression and logistic regression for classification. So what is machine learning? Well, it's effectively using computational algorithms to model patterns in data. This is like deceptively simple definition, but I asked ChatGPT about this and it agreed with me. So let's look at linear regression. I'm going to run this code to fit and visualize a linear regression model. All right, so here's our result. We can see a bunch of random data and it's pretty linear, and we have a nice linear fit through that data. Well, I used NumPy to generate some test data, and then we imported linear regression from scikit-learn. I instantiated that object and then fit it on our data. After we did that, I made predictions, and so then once I predicted those two data points, I just plotted those using a line. Let's look at some of our variables here. So for x, for example, we can see x is a list of lists. In this case, we're just predicting on one dimension. Y is, in this case, also a list of lists. There's just one target variable. What I could also do is look at my x new. Those were just those two data points that I wanted to make predictions for. And when I did make those predictions, they were just going to be 4 and 10. All right, let's move on to the next example. This is going to be another supervised method, so we have labeled data that we're modeling, but in this case we're going to do classification using logistic regression. Run it, we're getting perfect accuracy. It means we're overfitting our data. But let's look at how we did this. We're loading an iris data set, and then we're going to grab the x and y data from that data set. Here's what x looks like. This time we have more than one dimension. There's 4 dimensions. And then the y, in this case, we just have a list of items. One-dimensional data set. There's 3 classes here. 0 class, 1 class, and 2 class. Hop up here. Now I do a train test split. I'm going to split our data up into a test size, which is 30% of the data. And that's it. So for example, xtrain looks like this, and xtest is going to look like the same thing, but the size of these are going to be different. So xtrain.shape and then xtest.shape, we can see that this is going to only have 45 records, whereas the training data had 100 records. Next, we instantiate our logistic regression model, and we fit that, and then we make predictions on the test data, and we get this y-pred out. So these are our predictions. And since we have 100% accuracy, that means all of these are perfectly correct. A better way of doing this would be using k-fold cross-validation. Rather than doing a train test split just one time, we'll do many different train test splits and build a bunch of different models on different parts of the data. And this will give us a more realistic scoring metric, and we'll also be able to get a standard deviation. So next we're going to look at our final supervised method, so where we have labeled data, and this is a decision tree. We're going to build and visualize a decision tree right now. So this is the decision tree we built. In this case, we're splitting on something called the petal length. And if the petal length is less than 2.45, we're going to the left side. And if the petal length is greater, we're going to the right side. And now we split again on petal length. And then we're continuing to split on different variables where the color of these indicates the dominant class at that point in the split. Picture at the top of our funnel, we're putting all of the data in here. But each time we make a split, the data is going different directions. And at this first split, we were able to pick out all of these Setosa classes just on this petal length feature. And we see all 31 samples of this setosa go into this bucket. And so we know that that's our class. That's what we're going to predict for that type of feature. But this one, we have a mix of the other two, and then we can see the greens correspond to this versicolor. Virginsa are the purple one. The shade is going to indicate how confident we are in that class prediction at that point. I love decision trees, and this is like a beautiful representation. We're also seeing perfect accuracy on our small sample data set with this decision tree. In practice, you would want to use something like a random forest or maybe a boosted decision tree ensemble model, because those are going to be more resistant to overfitting, and they'll give better results. So lastly, let's look at an unsupervised method, and this is going to be KMeans. So we're going to imagine a bunch of data where we don't have any labels on it, and we're going to say, just create me some clusters. I want to just find patterns in this data. So if I run this, here's our result. We can see in our sample data, there's clearly a cluster up here. There's kind of a cluster here, and there's a cluster here and here. So we've picked out 4 different clusters based on this data, and we've indicated the cluster centers with this little red dot here. And that's what the K-means algorithm is going to do for us. Generating some synthetic data. This is just going to be our training data. And now there's no reason to do like a train test split in this case, because I just want to give it all of the data and say, figure it out, find me some patterns in this. And that's what I'm doing here. I'm feeding all of that into our model, and we're saying explicitly, we want 4 clusters. This is what we expect. This is engineered because I'm making 4 blob clusters. But what we could actually do is, let's change this around. Let's say we wanted to only find 3 clusters, and I'm going to instead here create more, like let's say 23. Let's see what this puts out for us here. All right, so now clearly our clusters aren't as well defined, but we can see our cluster IDs are pretty evenly spread out over the data set. We have one here, we have one here, and we have one here. And that's pretty much what you'd expect. Now clearly these don't, like this one here, I mean, you can pretty clearly tell that the IDs don't correspond well to the actual like clusters available. And I'm sure there's more advanced ways of analyzing these models and determining how well they did fit the data. For example, in this case, it's definitely true that we should have used 23 clusters. That would have given us the most optimal fit. And so there's ways of analyzing these models for how well they're fitting the data. And so then lastly, we can get some information out of the model, like the cluster centers and the cluster labels. And that's what we're using in order to generate our plots. Centers, and these are our centers in our 3 cluster case. And the labels are the labels on our input data set. So I have all of these X records, and what it's gone ahead and done is it's applied labels for each of those. And those labels are based on how close they are to the cluster centers. That's the last model I want to show you. But before we finish the ML algos section, I'm going to talk about data pre-processing, because this is extremely important, and this is part of the machine learning algorithm that we need to do to train models. I have a big demonstration here, and again, I'm just going to feed all of this in. So let's make this a little smaller. I'm just importing some libraries, pandas and numpy. I have np.nance, so I'm inputting missing values into a sample data set right here. And we have data set about students and their education and salaries and occupations and stuff like that. And then I have this target variable. It doesn't mean anything in particular, but we're going to try and predict this. And we're going to try and predict, based on all of these features here, can we determine if the target is going to be yes or no. So the first thing I do with that data is to create a data frame, and then I'm displaying that. And in fact, that's what we're looking at down here. And now I'm importing various methods. We're going to define our X by just dropping the target and the ID columns and looking at everything else. And then the Y is just going to be the target. So for example, if I come down here, this is our X, it's a data frame, and this is our Y, it's a data frame series. Next, we're identifying the numerical and categorical features. Often I'll just do this manually, but here we're using pandas methods to do it automatically, which is really cool. So here's the numeric features, and it's a pandas index object. Categorical features are like this, and what you could go ahead and do is filter X on these. So now we're defining scikit-learn pipeline objects. These are a really useful way of transforming data, because then we can wrap up all of our transformations in this really declarative way, and then see how those impact the model, and then make changes to how we're transforming things, and then see if that produces a better model or not. And we can also do this in like a grid search fashion. Here we're saying for all of our numeric features, I want to input the median value, and then I also want to scale them using a standard scaler. So we're going to normalize that data. For the categorical features, I want to input these using a different method. There's no concept of a median anymore when you have categorical variables, or at least the analogous concept is your most frequent. I want to use the most frequent category and just put that in for the missing values. Looking at our example here, we actually don't really have most frequents except for gender. So this nan value would get filled with the male gender. These ones I assume would just be a random selection from the available options. Lastly, we're going to one-hot encode this data so that we convert it to a numerical representation. And now we're combining all of these into one pre-processing step. And I'm saying we just have these general transformers. We have some numerical ones, we have some categorical ones, and I'm just giving them IDs. We're doing a train test split. And then we're creating our pipeline. And the pipeline consists of this pre-processing step to prepare the data. And then we're going to fit a random forest classifier. And again, these are just labels. They could be whatever you want. But now, instead of fitting the classifier directly, I fit the pipeline. And when I run this fit function, we're just passing in the training data that came out of our train test split, but it's going to put it through all of that pre-processing as part of the fit process. Then we can just go ahead and predict with that pipeline. So we can actually see what the Y prediction was, and there was just one sample because our data was so small, just testing one thing. In fact, our sample we were testing was no, and we predicted yes. So our model has 0% accuracy. And we can go ahead and look at I want to look at the X test, and this is going to be the features for this sample. So that is a wrap on ML algorithms. As I mentioned in my first video, we're really just scratching the surface of each of these topics, and my goal is to give you a broad view from like the top down of all of this ecosystem, but also to give you enough hands-on examples that you look at it from the top down and don't just see it as like concepts, but actually see it as things that you can touch and affect and work with. I would appreciate it if you give this video a like and consider subscribing. This really helps support my channel. And another way to support my channel is to sign up for my newsletter, where I just send one email a week when I upload a new video. In the next part of this series, I'm going to be talking about parallel computing, REST APIs, Kubernetes and Airflow, and unit and integration tests. It's going to be a really fun one, so I hope to see you there. Thank you for watching, and namaste.